Hi, and welcome to lecture 33 in my mobile studio. I'm not going to be able to show pictures of my scribblings on a piece of paper, so I will attempt to explain this by using visuals from the assignment and also just in words. We've been looking at RAM computation, and last day I talked about how to use RAMs to implement data structures. And in particular, you can implement arrays or lists as arrays or vectors. And this is good and bad. If you have an array implemented as a vector, it's fairly easy to do cons and car and coulter, and it's equally easy to do listref. So you can go to random places in an array list in constant time. The downside, though, is that if you have several of these, you don't know exactly how many memory addresses to allocate to each list, and if you choose wrong, your list can overflow. If you don't detect it, that can cause really bad things to happen, and even if you do, you have to figure out what to do about it. So what I'd like to do is to have a look at assignment 12, which exercises RAM computation. So assignment 12, first of all, gives yet another definition of generate that I mentioned briefly already. Essentially, it's just like regular generate, only it has two state functions. It has an input stream, an input list in this case, since we're not lazy, and a state. And the state is this single RAM. And step is the computations you do one at a time, always manipulating the RAM in order to do the computation. So I mentioned that, and I mentioned RAM already. It's going to be implemented with a trie. I'll talk about tries probably in the next lecture. They may be useful to you in doing some of your assignment problems. But basically, with what I've talked about so far, you should be well set up to do A12A and A12B. A12A asks you to take a running sum of all of the elements in the input. So at any given point, your step function will consume one element of the input, and eventually it will output in one-to-one corresponds with the input, the sum of all the numbers up to and including the current one. Okay, so you can do that, and you're going to do it basically by keeping a list of the numbers you've seen before, because you don't want to add it to the running sum if you've already seen it before. A12B is basically the same problem, but it has different runtime constraints, and you can figure out what properties of a RAM you need in order to make that work. 12C has the same problem as well, but it has different running time again. It says O of n log m. I don't specify whether that's supposed to be the unit cost model or the log cost model. You can do this in the log cost model. It also doesn't promise that the inputs will be in random order. But basically, A12A, A12B, you have everything you need to know. A12C, you may find what I'm going to talk about in the next lecture useful for A12C. So today, to be assignment driven, I'm going to talk about what you need for the remaining assignments, D, E, F, and G. I added F and G after the fact, so I'm making those bonus problems. Each of problems D, E, and F, well, D, E, F, and G, involves programming in a new computer language that I'm going to call machine language. So here's the deal with a stored program computer. You have a RAM and you have a generate function called the central processing unit. But the central processing unit is really stupid. It can only do a handful of elementary operations, and you're going to have to use the RAM to control or to specify which of those operations it's going to do. So imagine you have a list of numbers between 1 and 10. You could say that 1 means add, and 2 means subtract, and 9 means multiply. And that's the basic idea of a stored program computer. You put a list of numbers in RAM, and that list of numbers is in fact a program in a programming language. The meaning of the numbers depends on who implements the programming language. When early computers were built, each one had a different programming language. That's still the same. So machine language depends on who built the machine. If you're using a computer with an Intel inside or a AMD, it probably uses a machine language that was based originally on a machine language that Intel designed, but then it was extended from, first of all, 16-bit programming language, where it assumed the words were 16 bits long, to one that was 32-bit, to one that's 64-bit. The 64-bit extension was actually designed by AMD, so they're an Intel competitor. But this is way more complicated than what we need. We need a really simple programming language, really simple machine language. So you're going to have one that was, manufactured by me for the purpose of this course. And what we can do is click through to have a look at the definition of that machine language. So I'm going to cover this in two parts. First of all, I'm going to talk about those elementary functions. And in fact, this particular machine language has exactly 10, or perhaps it's 9. We'll figure that out as it goes along. And before we even talk about the machine language, which is how we tell the machine to do these things, let's write some helper functions. These are the helper functions that are actually going to implement the handful of operations in our machine language. So you can see this is implemented in a module that is called CPU.Racket. CPU.Racket is going to use RAM, and it's going to provide two functions. One is CPU. CPU is this elementary function, or this elementary program that steps through the machine language program. And it's also going to provide a function called RAM load. The idea with a stored program computer is that the program has to be in the RAM. And this raises a kind of a chicken and an egg problem. How do you get the program into the RAM? There's several ways to do this. You might, in the old days, you would maybe even flip some switches on the computer in order to put the information in the RAM. Or you might have a special program called a loader that would read from an input device and put the program into the RAM. This process goes by a couple of different names. When IBM built computers, they would call this an initial program load, or IPL. If you look at sometimes if you look at cash registers or business machines, you might see that they have a button on them called IPL. And what that means is load the program and start it running. It's like the start button. It turns out that a loader is in itself a reasonably complicated program. And often what you do is you load a really tiny little loader that loads a more complicated loader, and it's what actually loads your programs. This process is called bootstrapping. It's because the loader pulls itself up by its bootstraps. You do some trivial amount, a very small program, and all that program does is it reads in more of a program, and it reads in more of a program. And this is called bootstrapping, or bootstrap loading. And this got shortened in the mini computer industry to booting your computer, okay? And this has stuck as well. So, when somebody says reboot your computer, they're just saying reload the initial program that runs in your computer. That's all it means. Okay, so that's what a loader is. We're going to give a Racket implementation of both a CPU and a loader, and then you can write some Racket programs, and not Racket programs, machine language programs that are going to solve basically the same problems that you solved in 12A, B, and C. All right, so here are the elementary functions that we have in our machine language. First of all, add one. All of these are going to be called CPU dash something. So what add one is going to do is it will take a RAM, obviously, and a target address. So if you see using the shorthand notation that I introduced in the last couple of lectures, it's going to take whatever value is at the target address, add one to it, and replace the value by the value that's one greater. So it's going to add one to the value at a particular RAM location. So there's trivial operation number one. Slightly more trivial, less trivial operation is add, which has two arguments. Well, it has three. First is the RAM, that goes without saying. And then you have a target address and a source address. So rather than adding one to the value that's at address, target address, it's going to add the value that's at the source address to the target address. There you go. CPU subtract. Same basic thing. It's going to subtract what's at the source address from what's at the target address, but there's one gotcha. We only have natural numbers. So if you're going to subtract, if the answer would be negative, we're going to put 0 in there. This is how we're going to do the equivalent of if with our elementary operations. So what happens is we have a target address, as usual, in the RAM, and we have a source address. But rather than adding the source address or whatever, we're going to take the value at the source address. And if it's 0, then we're going to add 1 to the target address. So it's a conditional add 1. It's like CPU add 1. It adds 1 to the target address, but it only does that if the value at the source address is equal to 0. And you can see the implementation here. Okay, now we get into the pointer chasing and copying operations. CPU copy, again, has a target address and a source address. In the RAM, it takes whatever value is at the source address and copies it on top, replacing whatever value is at the target address. CPU fetch, here's where we get indirection. We still have a target address and we still have a source address, only it's a source pointer address. What this says, go to the source pointer address, take the value, that gives you another address. This is your scavenger hunt. That gives you another address, and then you should fetch from that address and store whatever value you fetched at the target address. So this is how you do pointer chasing. If you want, the car of a value or something like that. If you want to go indirectly from a variable, and that variable has the address of another. CPU store is kind of the inverse. You have a value whose address is in the source address, but you want to store that not directly at the target address. You want to go to the target address. The target address will give you a pointer. It will give you the address that you're really supposed to store it. So that's where the double bracket notation comes in. Then we have our input and output stream. CPU output is just going to take whatever value is at the source address and append that to the output stream. And the way I'm going to implement is just with a display in a new line. Input just goes to the input stream, takes the next element of the input stream, and stores it into the RAM at the target address. Okay, so those are the only operations that we have in order to write programs, but they're sufficient to write any program you can write with the Lambda calculus or with any other Turing complete language. Let's just very briefly look at the loader. The loader is magic. If this was a real computer, we would say, hey, hardware designer, please give me a way to get some data into RAM at specific locations, and they would obligingly do that for us. So RAM load, again, takes a RAM, takes a load address. So this is going to load all of the numbers in list into RAM in consecutive addresses starting at the address given as load adder. And it's just a simple recursive program that takes the elements of the list one at a time and copies them into RAM. So here's the idea. I'm going to switch right to the bottom of this code, and I'm going to show you how it works. So here's an example. RAM load into RAM at address 0, and then we have a list. This is our actual machine language program. This tells the computer that what I want to do is something. Well, what do I want to do? It's actually a pretty useless program. It takes one element from the input stream and puts it in RAM at location 99. But if you run this program, when you run it using the CPU, then core dump, you'll find that it has put a 99 into that particular location. Okay, so that's what it does. Okay, now I've switched to Dr. Racket, and we're looking at the same program here. Let's run it and see what happens. Oh, remember it inputted a value. So let's put in 1,001. Okay. And remember I said that it copied the input value to location 99. So you can see 99 contains 1,001. But so does address 1. That's in fact where the input command put the value in the first place. Now, these numbers are pretty cryptic. How do I translate these numbers, or how do I ascribe meaning to these numbers? Well, we look at the Rosetta Stone above. This is the answer key. Okay. So the machine language program is just a list of numbers. Each of those numbers is considered to be a 5-digit, or is interpreted as a 5-digit decimal number. Okay? So when we look at the digits, the first digit is an indicator of which of the elementary operations we want. Second two digits, TT, are the target address. So when you do, for example, 0, which happens to be add 1, you specify TT, which is a target address, so it will fetch the value at address TT, add 1 to it, and store it back at address TT. So that's what that means. 1 is add. So it takes the value at address TT, the value at address SS, adds the two, and stores at TT. Now, by nature of the way that the TT and SS are encoded, each of those is a two-digit number. So it can be between 0 and 99. So whenever you do add 1 or add or any of the other functions, if you have a target or a source argument, that is necessary. You have to pick a number between 0 and 99 as that source argument. So that's how you're going to encode instructions. And you say, that's fine, but what if my program has more than 100 things that it wants to store? You told me RAM can be arbitrarily large, and it can. But in order to use any RAM beyond the first 100 addresses, you're going to have to use the indirection commands. So let me briefly go through these commands. 0 is add 1. 1 is add. 2 is subtract. Remember, it takes the target minus the source and the maximum between that and 0 so that you don't have negatives, and it stores it back at the target address. 3 is just the copy. It takes whatever's at the source address and makes a copy of it at the target address. This is the conditional add 1. So if the source is 0, then it adds 1 to the target. Otherwise, it does nothing at all. Here's the indirect, the memory fetch. We take the source address, which has to be a number between 0 and 99, but then we fetch the contents of RAM at that address, and that can be any number at all. So if you want to access RAM location 1 billion, what you do is you arrange to get 1 billion in one of the RAM locations, the number 1 billion in one of the RAM locations 100 or less than 100, and then you use indirect. And this lets you fetch what's at 1 billion or any other arbitrary address that you care to compute. And similarly, the store instruction lets you put an arbitrary value into RAM and then use that arbitrary value as an address to store, or where to store stuff. 7 as the first digit means output, adds the contents of RAM at address SS to the output stream. And 8 consumes a value from the input stream and stores that in the target or in RAM at the target address. And last, we have this funny instruction called halt. Halt just means my program is done. CPU can quit. And in this case, we have the RAM value left over, and we can look at it with core dump. So there's two ways of getting the, if you like, the result of the program. You can either just use core dump to inspect the result, or more likely, you're going to put the result into the output stream. So now you've got a program that reads from the input stream, consumes the input stream, and produces an output stream, having done some computation on that. All right, so that's the basics of the machine language. That's how you can do elementary computations using machine language. But we still haven't actually talked about how to do recursion. Now, in machine language, you cannot do general recursion. The only kind of recursion that machine languages generally support is tail recursion. And tail recursion in the CPU or in the RAM world is typically called looping. But it's the same basic idea. You have executed a step, you have updated RAM in order to reflect whatever computation you're trying to do, and then you want to do another step. And the way you do another step is by telling the CPU, would you mind just doing that stuff over again? We've had this concept for years in music, for 500 years. You have notations that say, okay, repeat the previous so many bars or lines or whatever. So that's basically what we're going to be able to do. But we're going to do it a little bit more crudely. In order to talk about how we're going to do that, we're going to have to look at the equivalent of the generate function, right? This is how you encode the particular instructions, the particular elementary computations, but how do you put them all together to form a program which is a potentially infinite sequence of these things that is going to do the computation you want. In order to look at that, we'll go back and look at the actual definition of CPU. So here's CPU. CPU takes as a parameter a RAM. Okay, that's where your program is supposed to be. It also takes as a parameter an instruction pointer address. Okay, so the instruction pointer is a variable that the CPU uses to decide which instruction it should execute next as its step function. Okay, so if the instruction pointer contains 10, that means the CPU will go to address 10. It will fetch the value at address 10, and it would use that value as the address of the next instruction that it should fetch from RAM and interpret according to these particular, after decoding the number that encodes an instruction. So the instruction pointer address is the address of where you find the instruction pointer, but the instruction pointer is itself an address of where you find the next instruction that you're supposed to execute. So let's look what happens. So RAM or CPU is just going to use this tail recursive helper function called cycle. You may have heard the term CPU cycle. This is the basic idea of what it is. It is just a tail recursive function that basically does one operation and then does tail recursion. So let's look what happens. So the first thing we have to do is we have to figure out what the instruction pointer is. Remember that the instruction pointer address is a RAM address that contains the address of the instruction pointer. So the instruction pointer itself, you get with a RAM fetch. Then the instruction, you get with another RAM fetch. So this is a double indirection, square bracket, RAM instruction pointer address. So that's what it does. The next thing it does is it adds 1 to the instruction pointer. This is important. the CPU uses the instruction pointer to decide what instruction it should interpret. It then queues up the next instruction. This is going to be the default behavior. This says, I, as the CPU, am going to execute the instruction at the instruction pointer. I'm going to add one to the instruction pointer so that the next step, unless somebody changes the future, I will execute the instruction following that instruction. So the default is going to be, I'm going to execute instructions consecutively in RAM. All right, then I'm going to decode the instruction. Remember, the first digit is the code that says which of these 10 operations I want to do. That's called the operation code, or the op code. I'm going to get that by throwing away the bottom 4 digits. I'll do that using quotient. If I divide by 10,000 and throw away the remainder, then all I have is the operation code. The target, well, if I divide by 1,000, I'll throw away the source, the 2 source digits, and then if I use modulo or remainder, it doesn't really matter which, I can, modulo 100, I will get a number between 0 and 99, which is the target address. And similarly, if I just take the instruction, remainder on division by 100, I get the source address. And if I need to debug my CPU, I can uncomment this print statement that will print something for every time it's going to execute an instruction. And then there's a fairly simple cond. If the opcode is 0, I do add 1. If the opcode is 1, I do add. If the opcode is 2, I do subtract, and so on and so forth. So once I've done all that, for all of these instructions except for the halt instruction, I just do a tail recursion. And my tail recursion is done with cycle, and I just alter the RAM so as to implement the desired operation. So that's how the CPU is implemented. Now that we know how the CPU is implemented, I can tell you the trick for implementing recursion and conditionals and things in your machine language program. Remember that if left to its own device, the CPU fetches the instruction pointer, adds one to the instruction pointer, and then interprets the instruction. If the instruction changes the instruction pointer, then the next time the CPU does an operation, it will go to that modified version of the instruction pointer. So if you want to skip over the next 10 instructions, you can add 10 to the instruction pointer. If you want to go back 100 instructions relative to where you would have gone, you subtract 100 from the instruction pointer. Or if you happen to know that the next instruction you want to access is at address 199, you can arrange to copy 199 into the instruction pointer. Okay, so you can go forward by adding to the instruction pointer, you can go back by subtracting from it, and you can go to a specific address by just arranging to put that specific address in the instruction pointer. So that's all there is to transferring execution to a different place in your machine language program. So generally what you're going to do is, well, this is another useless program, I suppose. So if we look at what this program does, we can paste it in. We have CPU R10, that's going to load it at 0, or we've loaded it at 0. And now we'll run it. You see, the first thing it does is it outputs 84. Why does it output 84? Well, there's this out instruction. And it says out whatever's at memory location 1. Well, what's at memory location 1? In order to know what's at memory location 1, we have to trace through the program. So the first instruction is 2. So this is the first instruction it's going to implement. This says go to address 1, take the contents of address 1, which is 42, and then go to that address. So go to address 42 and copy the contents of address 1 there, which is a really complicated way of saying place 42 at address 42. Then this instruction is an add instruction. It says add the contents of memory location 1 to memory location 1. Remember, it was 42, but now it's going to be 84. And here we get to our output instruction. The output instruction outputs the contents of memory location 1, which by now contains 84. The second output statement outputs what's at memory location 42, and we know that that's 42, so there's our output. Then we take the instruction pointer, which is at location 0, and we save it. We copy it to address 44. So we're going to save the instruction pointer. What's the instruction pointer? It's going to contain the address of the very next instruction, because that's the way the CPU works. So now we're going to read a number from the input stream, and we're going to put it at RAM address 55. So let me type 897 as my input. That puts it at memory location 55, and then immediately outputs it. So here's the 897 I typed, and here's the 897 that's output. Then it says if 55 is equal to 0, then what we want to do is we want to add 1 to address 0. Remember, address 0 is our instruction pointer. So this says that if the number I type in is 0, I'm going to add 1 to the instruction pointer. So the next instruction I'll execute is going to be a halt. But it wasn't a 0. So I'm going to go on to the next instruction as normal. And here I'm going to store at address 0, that's the instruction pointer, I'll copy whatever's at machine address, at RAM address 44. And if you remember, RAM address 44 was last stored there. And that will be the very next instruction after that, which is the input instruction. So this resets the instruction pointer, so you go back and you read another input. And we can do this as often as we want. If I type 777, it'll print that and ask for more. Another number, it will keep asking for more until I hit 0, and then it stops. And you see the result is a wrapper. Well, the result is really a RAM, and if I wanted to see the RAM, I would have had to say core dump of CPU R10, and then I do it all over again, give it some input. And then when I look at the RAM, I'll see there's the instruction pointer, which is 12. Remember, address 1 started out as 42, but I doubled it and it's 84. Here's my program, ending with the halt instruction. Here's the 42 that I stored at address 42. Here's the instruction pointer that I stored at address 7. And here's a 0 at 55. That was the last element from the input stream that I ran. All right, let's look at one more program, perhaps not in this much detail. Here is a program that sums the numbers from 1 to n. My favorite program. So what this program is going to do, first of all, the instruction pointer is going to be right at the beginning. It starts off at 6, which says this is the first actual instruction. Then I have a bunch of variables. Constants are called literals. So I'm going to need the constant 1. I'm going to put the constant 1 at address 1. I'm going to put the constant 2 at address 2. I'm going to put the constant 7 at address 3. And then I have 2 accumulators, n and ac. Well, n is the number that I'm reading in, so it's the next input. And ac is my accumulator to sum the numbers. So I'm going to input n. I'm going to store, I'm going to read the next input, put it at address n. If the input is 0, I'm going to skip the next instruction. The next instruction skips 2 more instructions by adding 2 to the instruction pointer. So if I skip that, then I'm going to output the accumulator. If I'm going to skip the next, so I'm not going to skip the next 2 instructions. So I'm going to output the accumulator, and then I'm going to halt. Otherwise, I'm going to skip here, and I'm going to add n to the accumulator. I'm going to subtract n from 1, and then I'm going to go back 7. Okay, back 7 from the next instruction. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Which is going to check again to see if n is equal to 0 and do this whole thing again. So I'm going to keep adding to the accumulator and subtracting 1 from n until n is 0. Finally, when n is 0, I'm not going to skip this the second skip instruction. Sorry, I am going to skip the next instruction, and then I'm going to output the accumulator and halt, as I mentioned earlier. So if I run this program, see, it's going to load the program, and then it's going to put the RAM in R. But let's do it first. So let's supposing I want to sum the numbers from 1 to 10. I'll enter 10 here. It outputs 55 and it quits. And if I want to look at R, I can say core dump of R and try to reverse engineer what happened in my program. In the bad old days when people had to program in languages like this, core dumps were really an important part of trying to figure out what went wrong. It's the forensic evidence for what went wrong with your program. I recall in my first summer co-op job, I worked for the Manitoba Government Computer Center, and there I worked on their payroll system, which was all written in assembly language, which is a close cousin of machine language. And some table of something, unemployment insurance codes or something, had been coded in that program as an array list that had a maximum size of 80 or something like that. And it had crashed the program because it wasn't big enough and it overran into the next thing. So they called me in at 3 in the morning and they said, this payroll has to run before 6. Fix it. And they gave me a stack of paper 6 inches high, which was a core dump of the program. But it was sufficient to see that where this table was supposed to be, it had overflowed and overwritten some other stuff that it shouldn't have. But then I had this dilemma because I only had 3 hours to get the payroll to run, and it took a while to compile and run this program. I didn't have any opportunity to test it. So what I did was I just made the table a lot bigger and ran the program over again. And, I filed a note that said, you really should re-engineer this program so it doesn't depend on having a fixed limit on this array. But I'm sure nothing ever got done about it. And it probably crashed a few more years later. I really don't know because my co-op was over and I have no follow-up information. Anyway, machine language programming is very, very low level. It's not something we want to do by choice. What we want to do is we want to be able to build tools to allow us to express these programs more conveniently. The first thing we want to be able to do is we want to be able to use a notation that is closer to this notation in the comments than the number encoding. And something that simply does the number encoding for you is called an assembly language. So if you program in assembly language, you're really programming in machine language, but you're using a tool to help you called an assembler. But in an assembly language, you just write these, this notation, but you're still going to have to specify every instruction in the machine language that makes up your machine language program. The C programming language is just a teeny bit more advanced than assembly language. You can very well imagine how everything in C is translated into machine language. And in fact, if you want, you could see how it's translated into machine language. So C has been called the universal assembly language because it's not machine language. I mentioned machine language is specific to a particular manufacturer. But if you write something in C, it can fairly easily be translated into machine language for any machine language that you care to use. And that was one of the main reasons why the Unix operating system, of which Linux is a clone, became so popular, because it was basically written in C, and you could move it to all kinds of different computers just by figuring out how to write a translator from C to whatever the machine language of that particular computer was. Such a translator, it's just a program, can be written in any language, maybe Racket. It's called a compiler. So if you're dealing with a machine language or a stored program computer, it will have a machine language. If you want to write programs that are very, very closely specify what the machine language is, you use assembly language. If you want to basically specify it, but you don't want to learn the machine language, you can use C. And then people aspire to higher level languages that have things like modules and data structures and stuff like that. And there's a whole bunch of them that are that are really derived from C, which are very procedural. Do this and then do this and then do this. And then there are others that are derived from things like Lisp, that are the so-called functional programming languages that specify, here are the data structures and recurrences you need, and let the computer go figure out how to actually implement the recursion and so on and so forth.